The Sun will begin to change into a so-called red giant in around 5 billion years. Its outer gas envelope will expand, and it will engulf Earth and the other inner planets in 7 billion years when it reaches its maximum size and brightness. However, the situation for humans will become serious as early as the next billion years, when the Sun's brightness will have increased by around 10%. The polar ice caps on our globe will begin to melt, and the oceans will begin to warm. The water in the oceans will then slowly evaporate into the atmosphere, disrupting the climate. As water vapor blocks the Earth's infrared radiation, it will cause a rising greenhouse effect, similar to that seen on Venus, making our planet hotter and wetter. With the Earth warming by tens of degrees beyond its current average, the environment will become unfriendly to life. The oceans will be the sole safe haven where certain life forms may exist, but only for a few billion years. So we only have a billion years to come up with a solution: face extinction, migrate, or perhaps it is best to relocate the entire planet to an outermost orbit. Hello and welcome to Zeey. And today, we try to see if we can expand the Earth's orbit to survive. Subscribe the channel and follow us. After watching The Wandering Earth, a Chinese science fiction film in which humanity builds a series of giant engines along the equator to escape a larger and hotter sun than today, the Earth abandons its orbit around the sun and heads toward Alpha Centauri. Let's set aside the later storyline problems, which see Earth threatened by Jovian gravity, and simply examine whether the film's core premise, moving Earth out of its orbit around the sun, is even feasible. However, for obvious reasons, the idea of shipping Earth to Alpha Centauri must be abandoned. More modestly, we should consider shifting the planet to a closer orbit to the Sun than it already has. Using two calculations, we find that moving the Earth 0.5% away would nullify the effect of a 1% increase in the Sun's brightness, while moving it 5% away would nullify the effect of a 10% increase, what we expect in a billion years, increasing its average distance from the Sun from 149.6 to more than 164 million kilometers. To accomplish this, we would need to inject energy into the Earth, but where would we find it? We must keep in mind that the Earth is enormous. To move this quantity, we would have to put into our planet the equivalent of 1,000,000 times the cumulative energy created annually by mankind for a billion years. Several scientists have attempted, more for fun than anything else, the tough task of conceiving a reasonable answer, and many submissions have been received. For example, the required thrust could be divided into a large number of smaller thrusts. Something similar happens every time a space launch occurs. The drive that the engines give to a rocket to send it beyond the atmosphere is a thrust exerted on the Earth. Its influence on Earth's orbital velocity, however, is modest because the power of a single rocket's engines, even the largest, is insignificant in comparison to the planet's mass. Someone has taken the bother to calculate that 3 billion launches of something like SpaceX's Falcon Heavy fully loaded would be required to impart to the Earth the thrust required to extend its orbit by 5%. Apart from numerous obvious considerations that rule out this concept, creating and powering such a massive Falcon Heavy fleet would necessitate consuming a significant fraction of the Earth's mass and resources. An ion thruster, which is an engine that provides a gentle continuous thrust by blasting ions, typically xenon, out of a nozzle and accelerating them with an electrostatic system, may be a more cost-effective way. This is the engine that propelled the Dawn spacecraft on its incredible voyage to investigate Vesta and Ceres. In our situation, this would entail constructing a massive ion engine and locating it at an altitude of around 1,000 kilometers to keep it outside the atmosphere. To send thrust to the planet, the engine would need to be connected to the surface with super-strong beams. To extend the orbit to the distance of Mars, an ion engine capable of delivering a continuous push of 40 kilometers per second in the direction of the Earth's orbit would require only 13% of the Earth's mass to be turned into ion propellant. We would still have access to 87% of the Earth. However, the most fundamental approach for removing a celestial body from its orbit that I can think of is the hard way. You may recall how nuclear bombs were employed to deflect an asteroid on a collision course with Earth in the films Deep Impact and Armageddon. In the recent several years, space missions have been created that plan to employ, or have actually used, such as the DART mission, a kinetic impactor which is a projectile, to mildly deflect a tiny asteroid from its orbit. Unfortunately, if the goal was to shift the Earth's orbit, both nuclear and kinetic approaches would be impracticable. In reality, our planet's mass, at almost 6 million trillion kilograms, is so vast that any explosive weapon or kinetic impactor calibrated to such a mass would have the unintended consequence of destroying the Earth. One final option is to use asteroids and comets to drain orbital energy from the Earth in order to expand the Earth's orbit to the required size. The objective is to slightly alter the orbits of a large number of Kuiper Belt planets so that they pass within a few thousand kilometers of the Earth's surface and receive gravitational assistance from our planet. This is essentially the same mechanism that has been used in various space missions since the 1970s to speed up, and sometimes slow down, a spacecraft using the gravity of planets. The effect is actually reciprocal. Following the close pass, or flyby, not only does the spacecraft's speed change, but so does the planet's orbital velocity. The planet's orbital velocity decreases if the probe is propelled by the flyby. Only the mass difference between a spacecraft and a planet is so vast that the planet's orbital velocity is unnoticeable. However, if the flyby were performed by an asteroid rather than a spacecraft, the planet's loss of angular momentum would be considerably more pronounced. After enough grazing passes by asteroids or comets, the Earth's orbital speed might be slowed enough to increase the radius of its orbit to 1.05 astronomical units. Calculations show that the work to be done would be cyclopean even in this situation. Mounting solar sails of 100 square kilometers on each of the 100 million or more asteroids, placing them in millimeter-calculated orbits, and waiting a century would be necessary, with the huge risk of putting who knows how many of these asteroids on a crash path with Earth. Furthermore, a 2001 analysis found that it would take millions of near passes by Kuiper Belt planets half the size of Ceres to achieve the needed orbital change. As if that weren't enough, because it's not just the body's mass that matters, but also its arrival velocity near Earth, only objects with extremely eccentric orbits, that is semi-major orbit axes on the order of 300 astronomical units, would have to be chosen. This implies that hundreds of years would elapse between two close passages of the same Kuiper Belt body. Some scientists believe this is the best solution of all, yet it still appears to us to be an utterly insane proposal on par with, if not more than, the others. Not least because our preferred option is based on the utilization of a cheap and commonly used propulsion technology in our neck of the woods, sunlight, or radiation pressure. The system employs a solar sail firmly anchored to the planet and parked in orbit around the Earth at a distance of about 2 million kilometers, where solar radiation pressure balances the Earth's gravitational pull, oriented to deflect solar radiation toward the planet's surface. According to a 2002 research, photons from the Sun reflected by the sail toward Earth would gradually push the center of mass of the Earth sail system outward, modifying Earth's orbit. Unfortunately, it has also been predicted that to move the Earth 5% of its distance, a solar sail at least 3 Earth diameters wide, or roughly 40,000 kilometers, would be required. An enormous task, to be sure, but it appears to be less hopeless than the other alternatives presented thus far. It appears to be sufficient to purify the basic elements contained in a metal-rich asteroid 3 kilometers across. The nickel and iron from the asteroid would then be transformed into an 8-micron thick coating. The sail would be complicated and vast, requiring active control to maintain proper orientation and shape, especially in the face of perturbations caused by the Moon's gravity. To summarize, there is no quick and cheap means to shift the Earth to a different orbit at this time. On the other hand, we should not ignore the reality that tampering with planetary orbits can be extremely dangerous. The entire dynamic structure of the solar system is the ideal fruit of the planet's mutual gravitational pulls spanning billions of years. a delicate process based on orbital resonances. Changing something, even little, might cause major alterations in the orbits of the other inner planets, in unforeseen and perhaps disastrous ways. The entire inner solar system may be thrust into a chaotic state that is difficult, if not impossible, to regulate. That may be the strongest case for shutting it down and attempting to leave the planets alone. But what will happen in a billion years? Many people believe that the only way out is to terraform and inhabit Mars, which will have grown a warmer and more inviting climate in the interim due to greater solar irradiation. Prominent scientists such as Stephen Hawking have advocated for the establishment of colonies on the Moon or other planets to ensure that humanity survives any tragedy that wipes out life on Earth. Even if we ignore the terraforming issue, it stands to reason that the evacuation of all 8 billion Earthlings, no one knows how many there will be in a billion years, would necessitate the equivalent of 100 million spacecraft as large as Musk's Starship. Even if we could fire 1,000 rockets per day, it would still take over 300 years to relocate the whole world's population. It'd be like attempting to drain the ocean with an eyedropper. So there appears to be no answer, but instead of beating ourselves up, let us console ourselves with the fact that we are 100% certain that our species will become extinct far before that extremely distant deadline. Alright everyone, here's where the video ends. Thanks for watching, and don't forget to like, share, and subscribe.